You haven't met me before. My name's Carl. I'm the Associate Director for Humanities here in the DSI. I'm an English professor by trade initially, but for most of my time in computing world. So what we're doing today is really a deep dive into topic modeling with latent dirichlet allocation, a particular kind of topic modeling. We'll talk about topic modeling, just text classification in general, and then really dive into LDA. And whereas normally in the workshops we do a lot of coding hand-on while we go, it just takes too long to process and get any kind of result that looks meaningful. And so rather than have you guys sling code so that'll run fast with like one iteration through and 50 texts where the results are just gibberish anyway, what we're going to do is take the time. And it's sort of like a cooking show, but I'll just, be more lecture and discussion and show you results as we go. But my real goal here is that people leave here. Well, I'll get that and have a slide on that. So a couple just of the learning objectives here are that we understand what topic models do and the range of applications, right? And so they're not just for text. We use topic modeling to model features from image extraction, to do image recognition. There's a lot of basically anything you'll see as we go through that where you think there's multiple topics going on, and we'll get when we talk about mixed models, but there are other domains that aren't just text classification for topic modeling approaches. To understand the computational workflow of the topic modeling process. And really, I should have said in the human workflow too, there's a certain process that you have to go through. Things sort of have to happen in order. If they don't go in that order, then you end up with bad results. And so we want to understand what that is. We want to identify and understand the key algorithmic and statistical methods that comprise the topic modeling workflow. Okay. Here's where we start to get a little deeper into it as part of the deep dive. We're going to really look at what's under the hood of the topic model. How is it actually doing what it does, right? So most people, and this really isn't an exaggeration. I mean, I would venture a guess that 95% easily of the people in the world that are doing topic modeling have no idea what's going on under the hood. That's true of almost any machine learning process that happens, right? Somebody wrote this great library in R, Python, or whatever it is, right? If that's what you want to do. And, you look at the documentation, maybe you went to a workshop or talked to a friend or something and you did up some reading on what, how to make the code work. There's a nice tutorial online and you run it and it spits out some results and results look reasonable and you call it a success and go on your merry way. And that it really honestly describes the majority of science of work that's going on in this area. And I truly do not believe that's an overstatement. Because we see it in all areas of machine learning. People don't really understand what's happening, what those parameters mean, and how it's doing what it does. And this actually is one of my, I don't know, it's not a pet peeve, but it's something that I stuck on a lot. I don't care how complex a neural network you are talking about, or the most insane artificial intelligence algorithm running at Google or over at Lawrence Livermore today. There is no black box. It is only a black box because you don't look inside the box and understand what is happening, right? Somebody wrote the computer program that did that. A neural net, no matter how many layers it has, I can save every iteration of every single thing that happened on every layer if I write my code that way and go back in and do the math and follow that process exactly and see exactly what happened every step of the way. I mean, that's just a reality, right? And a lot comes from not understanding that black box. And when the result of this is the black box thinking, that's when we set ourselves up for doing bad science. For producing a result that we think is meaningful and isn't actually meaningful, it's just accidental. Right? Or worse yet, which we'll talk about, especially in topic modeling, is overfitting, which is what everybody does, is overfit their model. So part of that is we are going to identify the hyperparameters, the priors, depends on, for most of the lecture, I'll use the word prior, which is more computer science way of talking about that. We can talk about hyperparameters as well. These are the numbers that you feed into the LDA process before it starts. It's in the code, and they have, not surprisingly, a huge impact on what comes out the other side. And I actually meant to download some videos, and I just didn't have time to do it. But you could run through like lecture after lecture after lecture when people talk in machine learning or LDA. And even there's a great lecture from David Blah, whose code we're going to be looking at, who invented LDA, and he's published the LDA paper. And they get to this point about the hyperparameters, and the instructors always say something like, and it's really complicated, like figuring out how this goes, because we're in the middle, they're in the middle of some of the course. They'll say, so for right now, 0.2 is a good number that everybody uses, it produces good results. We'll just use 0.2 and move on so we can get to a point, and then we'll talk about that later. And then later never comes, right? It's just the common thing. So today is later. So all we're doing today basically is looking at that 0.2 and the other hyperparameters that go in, because my primary goal is that you leave here and understand how to tune your model, right? So that you can count on it being. And then we're going to identify tools and methods for estimating and evaluating the parameters in the model, right? So that instead of just looking at it and saying that looks good, we actually have some reasonable, valid, statistical way of looking at what comes out and deciding, is that a good or not, right? Can I trust it? So that's really what we're going to do. Some relevant information to that is that it's going to be, like I said, mostly lecture and discussions for coding, just because it takes a long time for these things to run. And so even the smallest data set that I could get in, where I could get some valid results and thing on my laptop, is still taking like 20 minutes, roughly each time. You just kicked off and waited, it wouldn't get a lot done. So it's not going to be as much hands-on coding. We will be doing that. Okay, so if you're not a mathematician, don't panic. Okay, because I'm not going to do gratuitous math here, right? I mean, in fact, I think there's only a couple of slides that have any kind of what looks like calculus on them at all, right? But we'll be talking about the math behind and walking through it. So don't panic if you're not big on math. I don't think, oh yeah, the notation. So where we do see some though, the notation and the variables that you will see, I'm using exactly the same one. This is always the problem, like with what notation you put in here. The variable names that I'm using are the exact ones that are in the LDA article, that canonized LDA, and that tend to be what people talk about most of it. If you leave here and you go to Google and you look these stuff up, these are the variable names you will see. So even if you're not big on math, it does make sense to familiarize yourself with the few we're going to look at and spend some time, because that will help you future forward in this world, because you're sort of inhabiting an of that community. And the working code, I don't know if you guys can see that, but it's at github.com, Stahmer. Probably all you need to know is github.com/Stahmer. Yeah.
Would there be samples for CPU or other the mixture model and the mixture model? So if there's only one membership vector,
We'll get there. I'm going to talk all about the mixture model and stuff like that. Yeah. So yeah, so Z is one of the variables we're going to use. Okay, so it's just github.com/Stahmer. You'll see a text mining with R repository. If you pull that down, it has some topic modeling scripts in there, right, that do all the things that we're going to talk about. But you really don't need them right now, but it could be useful after the fact if you want to go home and start playing stuff. Okay, so enough of that. So let's kind of dig more in. So I want to start with the backstory. Topic modeling is just thinking about document classification in general. So document classification here, according to Wikipedia, my friend, is a categorization of the problem of library science, information science, computer science. Task is to assign a document to one or more classes or categories. So pretty straightforward, pretty much all understand what we're talking about. We have some set of classes that exist in our world, and we want to assign documents into those classes. Right, so we have a set of documents, And we just say, okay, this one belongs to class 1, this one also belongs to class 1, this one class 3, et cetera, and we're happy campers, right, as we move forward there. Now there are all kinds, everyone's looking so far, right? You get the general brand? There's actually all kinds of document classification, right? We hear a lot about topic modeling. These are just a few methods that people use for component analysis, in fact, a nearest neighbor analysis, squared error, support vector machines, neural nets, deep learning. There's a whole bunch of approaches. The one we're doing is one which is known as topic modeling. It's a particular set of document classification, and it's a type of statistical model for discovering the abstract topics that occur in a collection of documents. Now, the one thing that I want to point out in those two definitions, and actually these definitions are quite good. But when we look at document classification, it's typically defined as the primary task if we have some classes and we just want to put the documents in the classes. We look at the topic modeling definition. What we get is that also is that we have to discover the abstract topics, right? So an assumption of topic modeling is that I don't know what these topics are when I begin, right? I just have a bunch of text, a bunch of words, right? So the idea with topic modeling is that we're adding a layer to this problem, right? Before I could tell you what text along topics, the real challenge is to figure out what are the topics to begin with. That's what we're actually modeling, right? And so hence topic modeling. We're building a model of the topics. The assigning the text, like figuring out which topics might be represented in which text, is actually the easy part of the problem once we know what the topics are. And we've been doing that kind of assignment for a long, long time with a lot of different methods, with text to classes, right? So it's really about the fact that we have a multi-layered system here where we first have to deduce the topics themselves, then we have to assign text to topic, okay? The other key thing about this universe, this crucial, is that it is a mixture model, okay? So it's a distribution. So if we think about that, what is a mixture model? In statistics, and I'll tell you what I mean by statistics, a mixture model is a probabilistic model for representing the presence of subpopulations within an overall population without requiring an observed data set should identify the subpopulations to which the individual observation belongs. Very long wording, but it's very accurate. What it basically means is this, okay? I can identify a bunch of my topics, a bunch of classes, right? So these, in this definition, are subpopulations, right? And then I have an individual can belong to multiple. So my whole population is all of these people, and any individual can belong to multiple populations here, right? And it's not necessary that I know up front when I first go into my analysis what all those subpopulations are. Okay, again, yeah. The answer is neither. It's a half neither. The reason I hesitate is because the model assumes that there is at least, that every document I put into it belongs to at least one topic, one category. Okay? That's an assumption, right? So it can't find a topic that then no document belongs to, right? But the figuring out how many topics there are is a big part of the community topic, right? So there are mathematical ways to estimate what those should be and to try to derive them computationally, but typically there's a heuristics involved here too, and you set a number of topics. One of the priors that gets set to the algorithm. So officially it is a prior, right? There are ways we can work outside the algorithm mathematically to figure out what we want to set that prior to. But it itself is not making it complicated. Yeah. Yes. Yes, you can. So we are in this whole thing is we mind will see that. It's we're in a probabilistic field, right? I mean, which, I don't know if we are, probably. Which mirrors our ontological reality, right? So, but it's an ontological universe in which there is no such thing as zero probability, right? Every single thing is probable, right? But we can tune this there's a couple priors we set, 3 priors actually make it all of them. We can tune this to change the shape of that probability. So I can make it so that a lot of those topics, approximate zero in the probability. Right? You can force a lot of things to get close to zero so that effectively there isn't a hit, right? But there will always be, and in fact, in the way this map actually pans out when we're done, in a probabilistic way, every single document is assigned to every single topic with a probability score. It's a matrix distribution, right? It's just that most of them will approximate zero in the probability. But do you understand that? Okay. All right, so what are the topics? Let's just start then conceptually again with so what are these topics of which we speak, right? To do this. And so in this particular case, I have these topics. I'm doing arts, budget, children, education. This actually comes, again, it'll look familiar if you pull the David Bly article. It's the example that he gives in the LDA article. And what topics are, is they are clusters of words. They're Bayesian bags of words. And here I'll say my little thing. This entire thing, we'll see the word, I think, in a few slides coming up. We are in a Bayesian universe here, okay? This is a Bayesian process. As how many people in here are in statistics in some way? Nobody. You do or do significant amount of statistics. So who may or may not know, there is controversy still to this day around Bayes. People will fight to the death in a ring over whether it's valid or not in any way. And I have absolutely 0% skin in that game, right? I could care less. I'm just putting all my cards on the table here, whether or not at a beautiful, pure mathematical level, Bayes should or should not make sense or work. We know from gajillions of trial and error and validation that the net result of this is it finds topics that work and allows me to classify text in a way that is meaningful. So from a practical point of view, this approach is functional and it works, and that's all I care about. Because I'm not a theoretical mathematician, right? So maybe there's a better theorem for Bayes someday. So I just don't get caught up in it. Bayesian, and whether it's a trick or not, it works. So our topics are constructed as bags of words. They're clusters of words, but importantly, they're clusters of words that co-occur in context, right? So a little bit of linguistics background here. One of the things that made this whole approach to working through language possible, and when we really started moving to NLP in general, was this guy Firth, philosopher, linguist philosopher, who has this saying, it's a sentence in one of his articles, that you know the meaning of a word by the company it keeps, right? Prior to Firth, linguistics run by this guy named Saussure, and everybody obsessed about signs, signifiers. And if I say tree, then you see the same tree in your head, and there's a lot of that for most of the thought around language that kind of universe. And what Firth says, basically, I don't care about language's relationship to the real world at all. That's a whole other kind of problem. That's actually not a language problem. It's somebody else's problem. I care about how words take on meaning. And in his mind, so it's very clear that words take on meaning relative to the other words that surround them, that are closest to them. Context is everything. And there's a tremendous amount of evidence now showing that how you learn language is that way. First time you see or hear a word, you don't know exactly what that is, but you know the context you heard it in, so you start to form some sense of meaning, and then you try to use it, and you maybe get it partially right or wrong, and slowly hone. And there's a lot of research on this. So the theory here is that we get a bag of words, and that bag of words is that these words are showing up frequently in context next to each other in whatever corpus I'm looking at. So better terminology, when I say corpus, what I mean is, and what we generally mean in the language processing world, is whatever group of texts I am examining in that moment, right? So I can have a whole library, a part of that library that I pull out and choose to examine, that is my corpus, right? I can subset my corpus for various validation and other things, but the corpus is the totality that I'm working on. So in some corpus here, we found that we had, I'm trying to remember where the first corpus is. Read the article? I think it's like Wall Street Journal article, some people, something like that we rely on. But anyway, we have a topic of arts, and what they found is when they read across all of these articles, that these words, new, film, show, music, movie, play, musical best, actor, verse, or opera, that they co-occur. They appear in the same context with each other frequently, right? These ones co-occur together frequently, more frequently than this way, and vice versa, right? So we have a topic here that a human is coming afterwards and called arts. This is crucial too, right? The computer is making we make no assumption about what this means, what it's meaningful, right? We're just saying it's a group of words, the computer's saying that. And then typically somebody else can make life easy to go afterwards and say, well, let's call that the art topic. Call this the children's topic, call that the education. So our topics are defined by just these bags of words that co-occur. And I'm going to talk later about chunking and what we mean by co-occurrence, because that also has large implications for that. But for now, let's just say they occur again. Okay. So then how do they relate to documents, right? And this is, again, the simple non-probabilistic way of looking at this. If I have a topic, and I have my chunk of text that I now want to say, is this topic represented in this text, right? And I put it that way purposely. I'm not saying, is this about this, right? Is this represented there, right? Because again, because this is a mixture model, and you can have subpopulations, there is a large underlying assumption here that's crucial to why topic modeling is so important, which is that in-text is typically always about more than one topic, right? That's what makes topic modeling such an attractive thing, because it reflects the truth on the ground, where almost anything you read is never about just one thing. And so brute force classification methods, they lose a lot of subtlety and supplements that we need. So topic modeling allows us to then go back and say, okay, well, William comes from the education, I'm trying to not this, but I've color-coded all of the matches to the topics to which they belong, right? And we'll get into the probabilities, but you can see right away, because every word really belongs to every topic, it just has a probability of how much it belongs to it, right? William actually is part of every one of these. It's a question of which one is it most probably, a part of, right? There's also a question, though, of in context here, right? So William may be most probably about children and not education. Let's say that it's out probabilistically, it's higher in the list for children and education. But the piece of text that I'm looking at is overwhelmingly, the other text words that are surrounding it are much more in this valence than I would say, okay, based on that, I'm going to actually assign it there. There's a higher likelihood now, given the overall profile. Do you understand what I'm saying there? Okay. So that is the whole process that we do, right? We run through, we're building our clusters. So first we are identifying our topics. We've got our topics, we map them to text, right? And then you typically write out a nice spreadsheet, and we'll look at some things that this says. Here's a text, this topic, 18%, probability, this one, 42%, whatever, right? You know, and we have this nice matrix that tells us what things are about, right? So that's the end game that we're trying to get. Everybody good? Just out of curiosity, whether you actually just a couple. Who here has actually run topic models before? Okay. What? Okay. Okay. Yes. Then who here is looking? You can have run them, but aside from running them, who here has actually had to look at the results, like to deal with the results that come out of the model? Okay, good. So I have. All right. So let's talk real quick about the high-level workflow that's involved in producing this thing, right? Some of it's obvious, and some of it not so much. Obvious first step is we have to acquire the text, right? And so for those that haven't done this before and think that this may be something that you will do as part of your research, acquiring the text is always much harder than you think it is going to be, right? We live in a world where we think, and I'll be totally honest, like for me, I was, how I ended up doing what I do was that in 1985, I sat down on the MILNet, the ARPANET, back I was in the Marine Corps at the time, and was tasked to send some do these database stuff with a put down a protocol for moving some data around. And somebody on there sent a text transcription of a New York Times article that came across. And I swear to God, it hit me and I was like, it will all be here. Like someday it'll all be here. And it just like, I was like, boom, you know? And I was an English major, right? And so it was like, I was like, you know, now I can read everything. And the internet that you guys, most of you grew up in, leaves you with the opinion that it is all there, right? So that it's just every text you could ever want to mine is there and you could go get. So people come in all the time with some project they want to do. And then, you know, we have to send them out heartbroken always at step one because the texts that you want to mine aren't actually there, right? Or you think they're there because you can go through the library website and go to Web of Science and JSTOR or wherever it is. You can find the article on Google Scholar and you can get some electronic version of it, right? But what you don't realize is that there's a license around that, right? So you hit a button, I mean, when you get there and it's got a license and you go to download, it says you can't, you know what I mean? Like you can only use it in this context, right? So, and then most of those, if you try to write a robot and scrape it, they kick you out, although you can get around that. You know, but at any rate, be aware that it's difficult. And it also, I should have actually part of acquiring, maybe I should have broken it out. Most of the time, you won't acquire it in the form in which you need it. It will come to you as a PDF usually nowadays, but the computer needs an ASCII text file. So you have to get it out of PDF and into text file, right? So there's usually a significant amount of work just getting your corpus at all, right? And so you should be aware of that if you're here because you're thinking you want to do this kind of research. You need to start earlier than you think you need to. Don't wait until the last minute, sort of thinking, okay, now I've got 3 weeks to go get this and run this analysis. You'll spend more than that just acquiring the text that you need. Then there's cleaning, and this cleaning step is the basic cleaning. Like anytime something gets transcribed, there's all kinds of junk and error in it. There'll be headers in it that are like every single page will say, you know, this courtesy came from JSTOR with this license on it or that, right? All of that is extraneous to the text that you want to mine. And if you leave it in, you know, maybe a couple sentences of header if you're mining 30 million texts, you know, maybe that disappears in the wash. Probably it does actually, the number of words, you know, text you have, but still out of clean, right? I mean, it's, you know, so you have to get it cleaned down to just the text that is the real text, not all the surrounding stuff. And you're going to have to always also look, and there's a bunch of code online that's there. When we finish, I'll just kind of give people a quick walk through the code that you get and show you what's there. You can go play. Whole workflow for like checking words in dictionaries, you know, making sure that actually what you have is real word text. Having just said that, though, I will say so. I just said something, real words, right, text. Topic modeling, the way that, it doesn't mean no word from a word, right? It will model anything, right? So it could be gibberish, and it sees gibberish twice, it's like, aha, pattern, you know what I mean? That, right? Picks it up, right? And maybe it's not gibberish, right? So there's all like word binding image stuff. It's not words at all, but we still treat it that way, right? So you have to make a decision also about what stays in and what doesn't stay in, what's meaningful and what doesn't. And that comes down to punctuation, right? So typically we would remove all the punctuation, but not always. There are cases where punctuation is actually semantic, right? Where people are, it's very meaningful that a word is the last word in a sentence, let's say, and you want to weight that in a different way than that same word, right, used somewhere else. We also in a lot of processes, this is a lot where we'll do part of speech tagging of the whole text first, because we really, really care about where something lives in a sentence relative to its grammatical structure, right? We want to claim that a word is different in a different place in the sentence, and we want to weight it differently, right? So you have to make those kinds of decisions too, to read stuff. But then generally we remove punctuation. We generally remove stop words, things like to, the, and then there's just standard libraries for that. They will, if you left those all in, on a decent enough sized corpus, they generally won't affect the model too much because they end up appearing like everywhere all the time, so they're not discriminators in any way from topic to topic, right? Because it's up there for everyone. But they're computationally really expensive then because it has to be dealt with every single time. And these processes are computationally expensive. So you want to be thinking about those kinds of issues. And so we generally will remove all the stop words, and you just have to make a research, question decision for yourself whether you care. If I'll give you just a little hacker's trick, it's a total hack, but this is what I always do. Let's say you can get all the top mountain factors that we have come with the stop word library, removing the stop words, right? You can just look at the whole list, see what it is right there. Maybe there's one of those things that you really care about, right? What you do is you run through the whole corpus with just a regex, a regular expression, and you replace that one word with like itself, dash, hyphen, XY12, like something that is statistically never going to show up anywhere else. You replace them all, then you remove the stop words, then you replace it back. Right? You just sort of protect it. It's it's a total hack. No one to date has ever shown me a faster way to do it. It's just a hack that works. Okay, now, lemmatized. This is an important one. I'm going to just make a guess that everybody here doesn't know what lemmatization is, so I will go over it, right? So when we have our words, say I am, you are, he is. Okay? These are all different tokens. So we talk a lot about tokens rather than words, but this I is a token, I'm a token, these are different tokens from one perspective, right? But topic modeling, sort of the way we normally use it by definition, topic in many ways, is more of a semantic exercise. Most of the time, we're trying to figure out when texts are about the same thing, not that they have particular matched patterns of tokens. And so this tends to get in the way, right, of the topic modeling. So in almost all cases, there are exceptions. I want to put it out there. There are exceptions where, especially for people who deal mostly in the literary side of the house, the stylistics, these type of things, where particular verb cases tend to be a mark of a particular author. They're used poetically in a way to actually say something very different. But most of the time, lemmatization is a process that changes all of those to the root word right? So if it was in my sentence, Carl was here, it becomes Carl be here, right? And you generally, most of the time, again, unless you have one of these edge case examples, you generally always lematize. There's another process that is built in, I'll tell people about this, and then we'll talk about the different ones too. Everybody good on lemmatization? Okay. There's another process called stemming. I don't have my slide deck, I'm not talking about it. You don't use it that much. And stemming does this. Stemming is a, let's say the word walking. We just knock off ing and turn it to walk, right? Stemming is a brute force algorithmic process. There's three, or really two, that we can use algorithms to use for stemming. And it's just a decision tree, it's a rule set. It's like what remove all S's. So if we go through, and the first thing is to take all the S's off. This is all the S's off. Free becomes free, you know, and it doesn't, and sometimes that produces something that is like this. And sometimes it produces a word though where S is like conscious. You take it out, and then you're left with a non-real word anymore, right? And so it goes through these series of steps, and actually does a pretty good job. It's a good estimation, a way of normalizing various versions of words. Walk, because EPs come off, so walking and walk, they both become walk. But consciousness and conscience, or being conscious, would not become the same in these numbers, right? Because the way stemming works. So it's, people do it because it's fast and it's easy to do. And so all of the topic modeling packages have a way that they'll be stemming, or they'll stem it for you automatically. My strong recommendation is that you don't use it, right? They use a lemmatizer instead. Lemmatization is way more accurate, does a way better job. It's based on these language models that have been built out by thousands of people over the last 30 years since we're started, right? They're very good. They come in, you know, multiple languages. They're available. So you just aren't going to get good results if you stem. It's not going to give you a good result. Yeah. Yeah. If you lematize. They alternate walk. Yeah. When you do, here's the one thing that is a problem. So you will get a better topic model if you lematize than if you just read it. You really will. The problem is from there on out, when you look at your text, when you human read your data, it at first glance looks a lot like yours because you're reading through all the lemmatized stuff, right? You're not seeing the real original. So you typically, when you have to keep track, we always are keeping track by file name and stuff. You have to go, often you have to read the raw data view and go back and look at the original document to start really making this, to read it again, because it is hard to read in 25. But the lemmatizers that are out there, the stuff that's in the code, it's code in GitHub repository, and there is code in the topic models packages in GitHub also. They do a really good job. Well, I mean, we don't say it that way because it's two totally different processes, but it does everything stemming with you and more. Right? It's a way to think about it. So you never do both. There's no reason to do both. But it's the preferred method. Again, people do there's a lot of in this universe, and I don't begrudge it. I do it. You know, we're dealing with so much data. right? That's kind of the theory. And it's pretty true. It's more true than you want it to be, actually. Right? You can have more dirt than you think when you're doing this huge scale, right? So that, and stemming is so much faster. And, stemming is so much faster. And that's why people play for like this thing. That's my recommendation. Okay, then we finally get to modeling, right? And the modeling, this is where we're going to spend most of our day today. Keep going, digging in details about actual modeling process. And then finally, we need to validate, right? And really, model and validate is a circle. They look back on themselves, right? The modeling process is always a process of validating, seeing what works, seeing what didn't, you got it right, that type of thing. So this is your overall flow. And the actual modeling part of the whole process here, really taking and modeling it, in terms of human effort, honestly, this is maybe 5% of your time. I mean, that sounds like it, but I'm not exaggerating. I mean, if your corpus is really, really funky, and so like your first attempts at modeling, which is way off base, then that can grow a lot longer. You have to do a lot more exploratory analysis to start to figure out hyperparameters and that type of thing. But generally, that part's easy. It's all the work you have to do around it that takes time. So real quick, I want to then talk about chunking. Okay, so let's go back. Just remembering that our topics are clusters of words, the Bayesian bags of words that co-occur, right? So here I have a page, a facsimile edition of an old book, because I do old books. And, it's got a lot of pages. It's a lot of words and all of these columns across all of these pages, right? So if I think now about co-occurrence of words, right? The question is, do they co-occur? Does the fact that they appear together just in a column constitute co-occurrence? Or does the fact that they appear together in the context of a single page constitute co-occurrence? Or does the fact that they co-occur, that they just exist in the same book constitute co-occurrence, right? I mean, this is a huge, huge problem, right? And I can tell you that co-occurring in a whole book will not give you a very good model if this is what you're trying to do, right? Because basically, once we put them in the bag, there's no information. And the algorithm itself doesn't really care where they appear next to each other as we're building our bags. So, I mean, like every word, over this many words in text this size, 50% of those words have equal probabilities of appearing next to each other. I mean, that's an exaggeration. I mean, I would guess probably something like 20% actually words in given text that of this size, right? And so that means your topics are very diffuse and very spread out that you're getting to. So it's not going to get good results. So decisions have to get made about whether you're going to chunk the text or not when you model. Now, couple things that you should consider here. One is overall length of text across the entire corpus, right? And that relative to question. Your research question is always in your mind. So there actually are times when I would just model on entire books, provided I'm always comparing whole books to whole books. Like I have all of my texts are within a reasonable size range of each other, right? And I'm asking a very gross question, right? I'm going to be modeling for a small number of topics. I know this already. I only care about something that's really as gross as like science and humanities, right? Or something like that, okay? And if that's really my mission in life, is just to do something that gross of its thinking, right? Then modeling the entire, and I tune accordingly to that. Across all long texts that are there, I can model across that. But if I have a whole mix of text, where some are one-pagers, some are really long, some are tweets, right? Then I'm going to have to chunk to get things down into a reasonable size of text, right? And as a rule of that, the general rule of thumb to put out there is that you should not have any text, single text, that is more than 4 times greater than the smallest text in the corpus, right? We want to get down to that type of a ratio, right? If you stay in that universe, your results are going to be pretty good. So if I'm going to put tweets in the books, what does that tell you? That means I got to do a lot of chunking, right? And that in itself is a very particular problem. I just gave you a rule of thumb. I said it's a rule of thumb, right? I will just say that people here, if you really want to do that kind of modeling where your corpus is that different, what we do is we actually layer Dirichlet layers on top of Dirichlet layers. And so we'll typically model like corpus to like corpus. We'll align the topics there, right? And so we align our models, and then we actually then build a global model that deals with these aligned models, right? And then we go through our work, and that will give you much better results. Because if there is a point, the reason why we do that is at the point where the tweets are so different. The language of a tweet, the syntax, it's a very different kind of natural language than what I would get in the book. So it has so many rules and engagement that are different that it has a lot of meaning packed into the 2 important characters now. Versus a book where someone knows they have a lot of room and tends to take a lot longer to get their full topic across, right? So in a book, people don't tend to jam 3 topics into one short sentence the way that people do in teaching. So the nature of the two different purposes means I can't really combine them. Does that make sense to everybody? So you have to do that kind of analysis up front. Yeah. The tweets, there's nowhere left to go. They're so small. Yeah. You couldn't really say it. A tweet sort of defines your minimal, mineable piece of text. Yeah. Yeah. But if I have like a book, I may break it up by chapter. I'm going to break it up by page. I'm going to break it up by paragraph. Right? And that all depends on what my overall set of my corpus looks like. Right? And again, in relation to the kind of model, what I'm trying to model, right? If I'm trying to build very supple models, if I believe that I want to model a universe that has 350 topics, right, across a bunch of, a bunch of books, let's say novels, right? I'm going to have to chunk it. I cannot read those as whole novels and get a good topic model with that many topics, probably, because in order for you to fit that many topics across the thing, you say, okay, like there's a section of the book that's about this kind of thing more. It's going to more represent certain topics, but then we're not going to talk about that for a couple chapters. And suddenly, right? So you have to know your corpus, and this is you see already there is a lot of like I said the word heuristics, a lot of the art, people who say art to these things, right? And there it comes with experience. The trick is to gain that experience by also testing the results, right? And that's the key thing. Like, you'll always have to make this kind of assessment of corpus. Like, what can I do? And you make a shot at it, you run it, you get some results, and it's about how you look at the results and what you do with what you see that then determines whether your heuristic is good. Right? Okay, now let's talk about types of topic models really quickly. We'll be moving from classification topic models. LDA, where we are, latent dirichlet allocation, was developed by David Bly. He was at Stanford at the time, now he's at Columbia. Really cool guy. That was like, that was awesome. And he's smart as hell. But prior to that built on prior knowledge, as we typically do. Really the first quasi-topic model, what people were starting to call a topic model, is a thing called latency and indexing. And latency and indexing itself, in 1990, you see the paper, it was a mixture model. It had a lot of the components that LDA has to it, but it was not truly probabilistic in the same way that LDA does, that we'll see in a minute, which has one mixture probabilistically on top of another mixture, right? So there's some debate, was it truly, it's not maybe truly a topic model, but it is definitely the beginning of topic modeling. Probabilistic latent semantic analysis, PLSA, sometimes just PSA, you'll hear people say most of the time, was the sort of immediate step before here. And PSA was truly a probabilistic multi-layered model. We're not going to do any of that. We're going to talk about LDA, and we're going to talk about LDA because it is the state of the art. And I will make a prediction that it is going to be the state of the art for a long, long time. And the reason for that is that it is very, very good at what it does, and what it doesn't do, provided you have a decent-sized corpus, can probably better be done with a neural net. So there's not with a neural net of some type, right? So there's not a huge incentive, actually, for huge research bases to try to develop the next better LDA, right? I mean, it's just it just really works for what it does. Eventually it will, and there are many use cases for this that will persist, actually. Mainly being that for the word-to-vec neural net model to work, you need a lot of text. This is kind of the great lie, and I'm going to use that word on purpose. The untalked about secret a lot in the world is we spend a lot of time talking about these neural net approaches, but the reality is that most of the research questions that people have, they do not have enough data for a neural net to work well. If you went around this campus, and we've done this, you see this in the DSI and data management, you go around and you look at the actual research problems. Most of the research problems, and most of on all fronts on this campus, are what we're now calling medium data. It's not big data. It's people working in labs, and they're producing what's a lot of data, but it's not really enough yet to where you can get good results out of the neural net, right? So this anecdotally, so I also work on image recognition stuff, and I have an image recognition problem where we use LDA, we do feature extraction, we build a library, yada, yada, and then once we converted it to this sort of bags of words that provide features of the images, we use LDA and start classifying, right? I just got back from this conference that in IBM, Facebook, Google, people from every major university. I mean, it was this small, but still, invite-only kind of gathering in New York. And, we were the only one that had anything working. And it's because everybody else is trying neural nets. And at the end, it was like, you don't have enough data. So I think we will use these for a long time. It depends on the size of the problem.
LDA is a precursor for block models.
For what?
For block models.
Yes, it is a stochastic model. Yeah, definitely.
And so this stochastic block model shows that if we have one LDA, it doesn't define boundaries to accurately. And stochastic block model that allows mixing of your blocks to actually allows better.
Yes. Right. Yeah. I mean, you can prove it. But that's still.
Are there any document like using LDA in such a setting that you allow the mixing of stochastic blocks?
Yes. Yeah. There are people doing that. And you do get better results for doing that.
Will that work better across a larger set of topics and a bigger topic?
Well, yeah, but see that now you just hit on the problem, right? Because then you ultimately that gets better as the size of the corpus grows, because it's growing on learning knowledge the same way a neural net would, right? Well, ultimately, you're at a point where it's like, well, why don't I just not now jumping over to a deep learning model, right? So there's this trade-off, and I don't personally know what that's probably computable, right? I mean, I think you could run some benchmark stuff and figure out, some parameters for that. You know, I don't know. You can see that that's the problem, right? Because I suspect that the normal would be better, you know, ultimately. Okay, so LDA. It's simultaneously not that complicated and yet complicated. I still have this thing about it all the time. What time? You can go on for an hour. Why don't we take 5? Let's take a quick 5-minute break. We can go to the bathroom, get a coffee. And we'll start back at 5 till. And this is a good. All right, let's go ahead and kick back in. Okay, here we go. Now we dig in. So what we're going to do is we're going to first talk about LDA process, the computational workflow, talk about the parameters, and then we're going to actually talk about how to tune them, what the effects they have, look at some examples, and you can go from there. So here's our definition of LDA. A hierarchical, Bayesian, generative, probabilistic model of the corpus, and its documents are represented as random mixtures over latent topics, where each topic is characterized by a distribution over words. Okay, that's the official definition from the article. If you unpack it, it's actually pretty clear about what this is. Again, so it's hierarchical. We'll look in a minute at those hierarchies, but because we're dealing with multiple levels, we have to model topics, and then we have to model topics across documents, right? So we've got topics across words, and then documents across topics. Okay, so it's a multi-level, it's Bayesian, it's generative, it's probabilistic. We've talked about all those things before. So I won't test you since we're not a room full of linguists, but I will get to the point that the latent part of this, the reason why it's latent, dirichlet allocation. The dirichlet is a mathematical process. Who knows when dirichlet ends? Something like that. Yeah, right. I mean, yeah, you know what I mean? It's been around for a while, right? This is the latent and the dirichlet combination is the key to this whole thing, right? What's latent in the model is the topics, right? We do not know what the topics are when we start. We're not coming into this ahead of time with that knowledge, so we have to discover those latent variables, right? What are the topics? And we're going to use primarily the dirichlet methodology to then allocate the documents to topics. Okay. Now, just as the thing here shows, we're assuming here that we have, if you read the article, effectively that documents are a Bayesian collection of words. And in this particular case, document means whatever my chunked unit of analysis is. So if I had if my corpus had a bunch of books, but I've chunked the books into chapters, and the documents are the chapters. Everybody with me? Okay? And that those are Bayesian collections of words. We're assuming a Dirichlet relation distribution of topics and a Poisson distribution of words within the topics to words initially, right? And I'm going to we're going to go deeper in a second to really what that means. I put some of these variables up here already. When we talk about words, we're going to be talking about W's. When we talk about documents, we're talking about D's, bigs and little D's, D's being the whole document set, D's being documents. When we talk about topics, we're going to talk about Z's, right? Again, because that's the way it is in the article, and that's most of the time, most of their stuff you read about, 90% overlap. You know what I mean? People will switch stuff up, but it's a good place to start with what's there. So, okay, first I want to take a step back there because not everybody is a linguist, and make sure we're all clear on just what a distribution is, right? So a distribution is, technically speaking, a function showing all the possible values of the data and how often they occur or with what weighting they occur or some factor, right? So in this particular case, if I take my 2 bags of words for my 2 topics, arts and budgets, my topic Z's, right? What I get here is a distribution for Z1, which is arts, that says that the word actor has a 0.008 probability, best has 0.089, billion has 9. And so this describes that distribution, right? So if I go across here, actor also has a probability for G2, right? G3. So this matrix across all of our topics will be what we call a topic words matrix, right? Which is very aptly, most people call it that, where we have a Z for every topic. And boom, you have every word in the entire corpus and a probability assignment for every word for that topic. Okay, that's your raw data after we've run the process. That's what the model. And really, that is the model. That's the topic model right there that you're looking at. Okay. So that's the kind of distribution we're talking about here. Now, having said that, and the same thing that would exist for distribution of topics in documents about topics. Right? We have another matrix that would list every document and every topic, and we have a similar thing, right? The key thing here is to note that these are their matrix. Each individual topic has a vectorized distribution, right? And the entire model is a matrix, is a collection of those vectors. Everybody with me? Okay. So yeah. No? Well, it's the distribution of Z is defined by this, right? Which happens to be a dirichlet distribution, but we'll get to that. But the distribution of the entire model, of the topic model, is the matrix, right? That is the combination of all of them, right? You have one, the chunks are no longer exist here. The chunks no longer exist. The chunks were used to get to this because they defined the co-occurrence of words that the model would walk through that, right? But at the end of the day, what you're left with is no representation at all of the chunks of text. What we just have is this giant matrix that just has every single word in the entire corpus and each of the topics and then the distribution. They go slowly. Yeah. 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 Regardless, right, exactly. But that number, like we just call it 2 over 1 million, right? But that's not really what it's going in, right? Because it's not a frequency count, right? It's the problem. This is actually, so in this particular case, this is going to really keep going. This is the probability of this word occurring with the probability of this word occurring with the probability of this word to comprise the topic that is Z1. They have a certain relationship of probability of co-occurrence, right? It's not, see what I mean? Because this has nothing to do with any text. It's not the probability that word shows up in the corpus at all. It's the probability that word, and it's not even, and you know, as we walk through the math, we'll see more what it really is. It's not even like the probability of actor showing up in topic 1, because that number is strongly related to the fact that actor occurred, you know, next to the word best in bags of words a certain number of times, right? So it's not a frequency count. Are you with me? Right? Okay. So those are our distributions. The same thing again. We have another one of these that's a distribution, same probability distribution for topics over text, and that's where our chunks would come back. As we'd say, right, go back. So it is what you're seeing is that it's a solipsistic model that runs in a circle. In fact, it does, right? Because everything, the words, we have words and documents. We have topics that are divided by words that depends on how they occur in the document. Then once we devise our topics, we're using the same words that comprise the documents to then assign topics to documents, right? So it has those multiple levels to kind of get back on stuff. Yeah. Yes. Yes. Okay. Here's the algorithm itself. We're going to go. Do you have any questions? Oh, it's the column sum. Yes, like you said, row sum. Yeah, the column sums 1. So each topic itself, so each Z, yeah, thank you, Emily. Each topic, these are the topics, these are the tokens, sums to 1, in its universe, like it has 0, always 0 to 1, right? I mean, so that's the case. It doesn't go across here because we're not making a claim about how often any word, the model doesn't care, it doesn't privilege the fact that a word could be in every topic or not in that way, right? That we assign one. Does that make sense? Every direction, right? It wants to be sort of free-flowing in that universe and say, yeah, a topic could be in every single text could be like that topic. Now, oh, totally. Yeah, it could be whatever there, but it's it's in our tuning that relationship happens. We tune the algorithm to see it. Yeah. This is a plus-minus distribution. If we look this one, we're having looking at the topics, right? The other one. Z1, well, Z1 is the topic. Is it art or is it? Yeah. Yeah. Right. So if I wanted to give that topic a meaning, what I would do, and we'll do some of this in a little bit, is I would sort these two columns on D1, right, top to bottom, and that would give me something that looks like this. And then I, as a human, think that and go, that looks like it's about the artist. And I would call that topic the artist. Does that make sense? Right? Then to get Z2, I have to then sort on Z2, again, making sure that the whole thing moves, right? And then I get my, and then I get list here, right? The most probable words. And that's typically how we assign a meaningful meaning to it. But you have to go. I personally think a lot of people don't like go far enough down this for meaning topics. And you really look at it. It just depends on what your probability distribution looks like, right? If when I sort this, and this again comes out of my tuning, but when I sort that, I could get a curve that looks like this. This is my top word, you know what I mean? Or I could get a curve that looks like that, right? Depending on how I tune it in terms of probabilities. So I can create a topic where there's really only 5 or 6 terms that have strong probability relationships, and everything else, you know, is very low. If that's the case, then I should really just look at those first few. So what you want to do is get to sort of figure out what your distribution looks like, right? And then when you're looking and comparing those distributions, that's which words are going to be meaningful semantics, right? Talking the same topic. Does that make sense? Yeah. It's weights. It's co-occurrence. Yeah, but it's multi-dimensional co-occurrence. It's not really those two words. It's these two words. It's group-wise co-occurrence.
I look at it from what is in general. I look at how often these words are appearing.
Well, the first, so it's, let me draw out a very simple, let me just use rough, more simple numbers, right? Think of these as weights. They're weightings. They're not frequencies, they're just weight, right? Let's just say that I have my Z1, my first topic, right? Let's take, let me take a word. And well, it creates some artificial values. sneak it out. Let's say that my words are Carl, Pamela, school, but then we need serve for sale. What do you do to your things? What I don't do. I could see, but I could see to do something else. Say press. We'll say press for sure, okay? Yeah. And then this could result in something that looks like this. Let's just say that I get Z1 and Z2, I end up with a 5, and I end up with a 1 over here. I end up with a 1 and I end up with a 5, right? I end up with a 3 and 3, I end up with a 3 and 3, I end up with a 4 and a 0, and I end up with a 0 and 4, and then I end up with a whole bunch of other words with 0, 0, 0. Right? So if this were what it is, what it's saying is, see, all of these words are showing up in both places, right? But in this very simplistic universe, right? Right now, I just have 2 topics. I would very quickly say, well, look, this is actually a topic about Carl, and this is a topic about Hannah. Okay? But now, let's say I have another pair, another topic by that again, right? And this is a very real scenario. This is exactly what happens in this scenario. Let's say even the word hobby goes up. And we also have down here, let's say baby, and silly, and okay. We could see another column that looks like this. It looks like, well, you know, include 1, 1, 2, some people think they say 1, 2, 5. These are way overblown numbers. 5, 5, 4, 5. Right? Now this is about, let's just say, hobbies. We decide, even though hobby is not like, let's make hobby not the top rated word, we can show up all the time. The most, see what I mean? So it's about these group, you know, really it's about similarity of the bags of words and things and things, right? Yeah, right. Yeah. Right. Yeah.
So you have all this, and then if you want to count yes.
Yeah, well, we're going to get into that. Almost all right, yes. I'm just saying, I think of this as ratings, right? And we're not, to be honest, we're not actually going to get all the way into it. If I showed you the full calculus for this, I mean, it takes an entire page to write it out. You know, I mean, it's the very, but we are going to high level walk through how it is getting calculated, right? So yeah. Okay, but now we all know. So we all know what's happening. Okay, so here's the high level way that this is. So remembering that so we just kind of actually dealt with the Bayesianness of it, right? There's some relationship with Bayesian between the bags of words between the corpus. The hierarchical nature of this is that we have multiple levels. So in this document, which everyone's still be oriented to, it makes no sense yet. I'm going to walk you through it. We've got plates. It's a plate diagram. We've got these replicates. So we've got one plate here. Our plate represents the document aspect of our universe, right? And then we've got an inner plate here, which represents our topics and the words within the document, right? They're plated because they're all resting ultimately on words. right? So that's the way this plate diagram looks. So look down, this W, which is where my words actually live, lives on both levels, right? It's common to them all. And what we say is this. This is the official, higher level definition for the DSI Workshop, that we choose N here, okay? Remembering that this inner plate is our topic medium level. We choose N, which is a Poisson distribution across real numbers. Basically, at this point, we're not saying anything other than it's just a bunch of real numbers, right? We choose here for our next level here, which is going to be our outer level, which is theta. You'll hear a lot about theta in this. We choose theta for dirichlet A, okay? Let me unpack that a little bit. The algorithm is going to use a dirichlet distribution that's going to give us a parameter that we have to give it to assign a theta value, okay, for words that occur on that document relative to then the inner plate, okay? So this theta is where you're heading. How the hell is that going to calculate, right? For each n words, okay, for each n, we choose wn, the word for that one, right? And this is our z level here. And what we do is we go zn, so that number, it is a multinomial distribution of thetas, right? Because those thetas relate to the words that belong there, right? So I'm telling you what it is, I'm not telling you how we got it. I'm just telling you what it is, right? In other words, let's see if it becomes its own vector of already computed values, right? And then we choose a word, wn, that's for the topic, and that gives us the probability that this word, right, has this topic, belongs to this topic, basically, given a theta prior. Prior we're going to call theta. So we're going to feed, so two things have happened. We fed a distribution to this right here, this theta distribution. So I'll work it now from the bottom up. And we've given it some idea, when we talk about theta in more depth, what is the likelihood that any word could belong to any topic? We've given it this map, basically. And using that map, it's making a prediction, saying what's the probability that this will be part of that topic, right? That's related in abstract to, because of the way this builds on itself, it's saying, well, what are the chances of other words being in that topic that I live next to in my chunk bed? Does that make sense? Yeah. So you do. That's exactly the thing, right? So this is the base thing. Here's really what this looks like. We do get a little more complex because we do. We've got a couple priors, and we have is a big K here, which is one of our big priors, which is everything here is basically the same, but we have to choose a K. We do have to choose a K. And what happens now is we're running through because we're giving it a prior right off the bat. Says how many Ks can it be? How many topics can it be? Right? So big Z is comprised of how many little Z's, right? So ZK, right? And then we have to give it a prior, which is what is the distribution of words within topics likely to look like to begin with, right? Meanwhile, over here, then when we finally get to our topic assignment, we're also giving a distribution, which is what is the likelihood prior that any given document belongs to any given topic, either in the abstract or specifically. And this is where earlier the question got at the very beginning, which is these priors, and we're going to break down and talk, I think, in the pretty much next slide, yeah. Think about the multidimensionality of our probability distributions, right? That means that these priors are multinomial also, right? There has to be a prior probability for every single word that it could belong to a topic, right? To start with, right? The prior. And so that itself is one long vector, right? If you got 2 million words, it's 2 million long vector. Now, when I get to how we tune these, we'll get to that. But is everybody in the abstract with me so far? Oh, it means that it's not, instead of just saying like my probability is, so like if it weren't multiple, I could just say there's a 0.2 probability that, so 0.2 that E word belongs to the E topic. Basically, it has to come down to the topic, because for every other topic, you just say, okay, but that would just be like, that's the project. You're saying 20% chance that anything belongs to the topic, right? That's not very useful, right? So, yeah.
The example, the example one probability, example, of the probability is of the two probability.
We didn't, because you know how it works. This is just a basic aside from LDA in general, right? So like, what we're saying here is we have one vector that is like, V1, V2, Vn, right? So we've got our Z, and then we've got, so that, I'm going to get okay, we've got a set of topics, okay? Z, which is our collection of topics, right? And let's just describe that as a vector, and it has Z1, Z2, Z3, Zn. Okay? Now, in reality, it's not a vector. It itself, because each of these is defined, V1 is actually defined by its own vector space, right? Which has Z1's definition is a W1, W2, Wn, right? Okay, that's what the real world looks like. Okay. Now we also have over here, here's a question about a multinomial, but okay. The other thing that we're asking is to define the document assignments, the distribution of the topic. So we've got our what are we clicking on our documents. N, the document here. Let's just go, yeah, so we'll stick with that. So we can, but let's say those are really comprised. We've got an N1, N2, N3, and N. Okay, and each of those is actually a collection of words, right? W1, W1, right? So far, this is what our data universe looks like, right? So if we want to assign, since topics are designed by words and documents contain words, and we're trying to get a product, right? We're working through, we want to assign that, and our algorithm demands that we upfront get some idea of what is the likelihood of it belonging to it at all is, right? Since these have dimensionality, right? And since there's multiple words, for every document, we have to say what is the likelihood of every word in that document belonging to this Z. And at the same time, the Z has these multiple words. So we're actually sending a flyer that doesn't look like to alpha equals, it actually is a vector of its own that is a value for V1, V2, V3, Vn, right? We're saying for this word, this is the probability, which is data for being words. And for this word, this is the probability that belongs to the topic. And for this word, this is the probability of this word. And if we were doing topics, we would be doing an output. But where we say, what is the probability that this, right? You see, that also, it's multinomial because we're sending it more than one. Not sending it.
And how is that multinomial? You start with two as a standard.
Yes. Well, yeah. So that is a really good thing. Hold that one for me. Okay. Okay, so let's go to the next one. So let's keep talking about priors. So again, in here, what we have, the priors that we've identified here, actually, like that slide. We've got an alpha, we've got beta, and we've got a K. Right? These are our priors. The beta is going to result is relates to the formation of the topic model. The alpha relates to the assignment of the distribution of topics across documents. Are we looking? Yeah.
So when you're saying alpha and beta, these are the standard
Or just blank variables for a value they're given a key, right? And that value, technically speaking, I say that technically speaking because most of the code nowadays will do some stuff for you. But technically speaking, it is always a vector. We have to send it a vector, we have to send it a probability for each item to be tested, right? In practice, all of them, we'll look at all the different packages here. All the packages that we use will allow you to submit a single number. And what it does is it just assumes that it converts itself and assumes you have flat probability, right? And often that's what you do, especially the first time around, because you have no way of knowing if you want to prioritize. But real quick, let's just talk about priors in general, looking on statisticians, like why this matters. Why do we care? It's mind's like, why? Why do we want to include this probability step at all? Why not just march through and see what I see, right? And start going. And here's a really good reason why. The simple explanation is predicting my batting average, which is very low because I don't bet it. Nor do I watch it. But it provides a very good, it's a good numeric example, so we use it. Predict my batting average. And so there are a couple key things about batting average for others that aren't baseball people, that it's calculated, it is an average, calculated as the number of hits divided by the total number of at-bats. That's the lifetime batting, right? So if you batted twice, you hit once, you struck out the next time, you would have a, say, 500, that's say 50% batting average, right? Okay, we know from prior knowledge, notice prior knowledge, that generally speaking, 266 is considered a good average. They're considered an average, and 300 will be considered excellent, right? No one's batting 500, no one's batting 1,000, right? And that's prior knowledge from watching lots and lots of batters over lots of time, okay? And we'll assume kind of this exercise that you actually right now don't have prior knowledge of my ability, of my batting. I have that, I can't bat, I mean, you don't know a lot about me. But you do know a lot about the rest of your universe, okay? And that matters, that's key, right? The global knowledge versus individual knowledge, right? So if I come here, there's a couple ways I could try to approach this, which are very unsatisfying. I could assume the sort of two-sided dice approach, it's like you hit or you didn't, 50-50, you roll the dice, right? You basically say your first time at bat, you got a 50-50 chance. Or here's the beginning of the season, and I'm going to predict what your batting average is for the whole season. Next time you come up with that, you know what I mean? Like you're not going to. This is going to give you like you got a 500 average. Like nobody, we know from prior knowledge that is not going to happen, right? So we see already prior knowledge of the large pile tells me not good. Okay, I can go and average so far. And so let's assume where you're at today, and then we'll just call that out, for the rest until we know better. Well, that's great. I'd start with 0% average, fine. But let's just say at my first at bat, I strike out. Then I'm going to make a prediction that for the whole season I'm going to have 0 average. No, that's not very likely. I'm going to strike out every single time. If I get a hit my first time, now I have a 500 average. Yeah, no. Although a guy that was actually a teacher of mine as a kid has the only perfect batting average in baseball, because he literally throw his bat on his first hit. Got to base, so he got the hit, and then he never played again. And that's an example of why that's that, right? So we use what's called a beta depth distribution for this statistical thing, and I'm not going to go into details of that, but it's the thing. It's basically you use your prior knowledge help you set a range, right? You say, basically, look, we know that most people are going to be 315, 316. You know the player gets out and strikes out at the beginning of the season in a trend, that they're probably not going to end up at the top. So that means the first time the person steps up the plate, I'm just going to call it average somewhere between 315 and 316. You know, that's the likelihood. That's much more likely than 1,000 or 0 or 500, right? It gives me there. And then after the first few hits, I can get better. I says, does this look like a strikeout trend? Okay, now I've got some math. I'm going to play closer to 215, not close to that range, right? So that prior knowledge really helps you actually make longer-term predictions. The way that I need this to, does that make sense to everybody? So in our topic modeling world, our priors, we do the same thing. I may not know something about my particular corpus, but a lot of people have looked at a lot of corpus, right, in the past, and we do know something about how words work and about how, in general, the world plays out. And that's where we get these kind of just general numbers where people start things, right? You just say, okay, yeah, let's just throw a 0.2 with, right? Let's call it 0.5. That's a good place to start because we know that's in the range of the reasonable prior. But what's twist about is it doesn't have to be that. And it's also really important, a lot of people forget going forward that it's polynomial when you send these priors in. It's not just that 0.2 or 0.5 or 0.02 that you're sending. So as you're modeling your universe, you may very quickly start to see that there are some topics that dominate your corpus, right? And if that's the case, you would want to flip out from sending a particular single number prior and start to adjust the model and say, look, I just know, like I'm modeling stuff from 1935 to 1942 or whatever the dates are. I'm not a 20th century historian. Like, guess what? The war topic is going to be prevalent in almost everything, even in the arts topic. That's what people write poetry about, you know? So I'm going to tweak that now. I'm going to run my model. I'm going to look at my model. I'm going to say, okay, based on that, for my assignment, for my document assignment, for my alpha prior, I'm going to change this up. I'm going to say, okay, no, this actually has a much higher. I'm going to weight that higher than that. Everybody with me? Okay. Again, keeping in mind that if I start weighting independently, now I'm in a process, right? I have to run it, I have to look, I have to go. But there's a way to test that also, which we'll hopefully get to later. But when we run, once I run a new model, I can validate that model by sampling on text, general rules that I didn't use to build the model, right? So you hold some out, you design your model, you run, you get your numbers, you get what you think is real, then you run the model on another set of texts, and then you sample those results and you human read, and you say, does this actually count, right? Does it make sense? Right? That's the way to go. It's cross-validation, exactly. So, and again, here, I really dumb that I left out this other thing. I actually remember the reason why I didn't talk about K yet. Because right now, K is a different order kind of prior than they're not these distributional polynomials, right? It's a different thing. But everyone's looking, right? So I've got one that I get to set that controls the formation of the topics themselves. I get one I get to set that controls the formation of the assignment of topics to text. Really good? Yeah.
In your war example, so with war topic then?
In that case, I was doing the war topics. Yeah.
Okay. And so you can assign probabilities to each of your topics. I can weight individual words and say like there's not a likelihood that this word shows up, in a lot of topics. There's not, right? You can tweak this model across the board. Almost nobody ever does. Some people put in 0.2, and assume an equal distribution. And given a good model, there's nothing wrong with that actually. It works really well as long as the rest of your team is good enough that you're giving iterations and optimizing it enough so that you can ultimately build towards a better distribution. And the point is just based on
yeah. Knowledge or knowledge of that particular, but that actually applies very particularly because it's a moment in history like you expect this one to just be totally across the board, right?
So like in areas where the field
I'm thinking that through actually.
this is, I do a lot of modeling in this field. Do I expect, I expect that individual words, yes, are going to be distributed across topics much more, right? Than I would at vocabulary rows. They have to, right? And they're like beginning to settle into the combination of yes, let's say that's true. So here's some just sort of tuning, some general points, and I'm going to kind of try to rapidly show this a little bit too, which is essentially, let's talk about, I just happen to have to do our alpha up here, right? But it really doesn't matter. It needs to be a number between 0 and 1. Okay, that's the way that is. And lower numbers will result in more, this is kind of what we were talking about. But if you tune this to be a lower number, what you end up with is a more sparse topic distribution. In other words, fewer topics per document. But either way, let's just say we're talking about the data. Fewer topics per document, or the word is going to be spread across fewer topics. Right? It's more sparse. And again, here, remember that they're polynomial, right? What I want to do here is just give an example of one. Let me kick out of here and try to get to, we can kind of watch this move around. This doesn't take forever. What time are we, what's our window? When are we, okay, good, we got some time. Okay, we're about right on time then, that's good. So let me go to Firefox. So I can't see my screen because my monitor is cracking as we speak. So I'm like, Firefox, okay. And let's look at this, no, not Markov Teams, report. I didn't open it in the PowerPoint. I'm trying to find a new tab on here. Can't see it well enough in here. I'm in trouble. Let me go to flip to it. I can't see it. Oh, there we go. Oh, it was getting hidden. It's hiding it when I go over there. There we go. There we go. Okay. This is a very cool little website. And we'll put the slide deck online on the DSI website so you guys can get to all these links. And it lets you, this guy's done this very nice little animation that shows if you watch the value of a change, right? This is not for LDA, but as the number is lower, so right now it's getting higher. This is our center point, right? As we get higher, we get more words start to push up. This is the probability factor, basically, that a word that's taking part of the topic, right? As the number gets higher, more and more words push up into the above 0 space. Does that make sense to everybody, right? And when it's very low, that's all like negative probability, the way we done math. And it's the corners where you get. You see very few corners in that distribution, right? So it's a triangular distribution there. And when it's at its really low point, basically the only parts that are living anywhere near some probability are just these very extreme corners, right? As that number grows, the middle starts to push up, because you get this umbrella. And if you just think of it as a plane, right? The surface of that is all of the words and their likelihood of occurring, right? More and more entering that equation. Does that make sense to everybody? So you can actually plot this yourself. It's very easy to plot. And there's even on the website, there's a place where you can play. And there's other links there where you can actually start putting in parameters. And you can start to look at how it will change shape for you, right? It's very, very useful because like you sort of think you know what a number is doing to that shape. But seeing it visually represented really starts to give you a better sense of like how restricted am I really making, right? You know, or how inclusive, like you're starting to get very nice double, that's a very even distribution. You know, that's like really very restricted, right? And then, so it's a good tool for figuring that out. Yep. So for something like this, I would base this most of the time not on the knowledge of the corpus per se. It depends on the kind of question you have, right? You come with a very specific question where I know I'm caring about a few particular topics, right? Then I would probably want to crank all the parameters way down, make it very restrictive, and make it, you know, again, sort of gross definition for just a few words to make any difference, right? Because that's the scholarly lens that I'm looking at, right? If your scholarly lens is more subtle than that, then you need to crank that number, you need to start changing the number, start cranking it up, right? So that you get more and more wider distribution, right? And so you really have, this is the art and heuristics of it, you do have to have a sense of your question and of the corpus that's there to some degree, right? Which you can only get after you sort of made your first run, some kind of analysis, right? Where you start to see like, yeah, that's unsatisfying, right? I really don't think, what you'll often will happen is you'll find a topic and you do that kind of really deep force thing, and you go, there's too many things in there. I need more, right? That's actually 2 topics in there. And so then you need to dial it back, right? Yeah, but it really is driven by your question more than anything else. There's no truth or untruth on that, right? Where it becomes untrue is if you ignore the other ones you created. So this is also my sort of like thing for how people, most of my problems, I have a lot of problems actually with topic modeling in the world, even though I love it and I use it all the time. It's the way people use it. And if you have, let's say, one topic, let's stick with like the war thing, right? And it has all these things that come right down, that include all these other things that are happening that are sort of about occupation, right? That aren't storming, beach, and Normandy kind of stuff. And you as a scholar decide, well, I want to separate those out, right? And so you now build, you make your model more finite, and you look at other topics that are closely related, but you've now created difference, right? If you don't tell me that, right, so that I can actually see your model and see that, well, yeah, but you have all these other things over here that by my definition, right, should have fit in there. I don't know how to read your results. Right, it's the same, it's a data collection problem we have all the time. Like, who did you ask, right, in your survey, right? So we really should be publishing our models, and people don't do that enough, and I really think somewhere we should. Like that model should be online somewhere when the paper goes in, so that somebody else can pull that out and look at the model and say, okay, like where are the bounds of that topic? That's what I'm saying.
And is that happen just for convenience reasons or for people trying to make
I don't think it's
stronger?
I think it's 3 things. I would also add some lack of understanding in the mix too, right? I mean, every case is different, right? And I think there's a lot of people who are like really well-meaning and want to be discriminating, and they shot the mark sort of wrong to begin with, and so they don't know if there was, if they should have been looking on the other side of that wall, and they would have been, that kind of thing. So that's just, they just don't know. But I think there are people who are quite conscious. It's like an audience. You're basically making up the result. You can make this. You can make any model. I can make it look the way I want it to look if I want to, and then what happens? We'll see as a one. We're really visualizing the topics. I can do that with malice. I can do it accidentally, right? Most of the time it's accidental, but it does happen. Okay, so that is the effect that these priors have, right? We're always becoming more or less discriminating in our universe. Let's scroll back to the PowerPoint. Let's go.
Take a second to roll back. I do know why it's so slow, actually, because I have this visualization. I'm going to show you some version of it. I was hoping to have ready for this class, where I actually tested some priors over like a lot of different scenarios. And I thought it was going to be faster than it was. It's going to run like 48 hours. I didn't want to kill it because now I want the result. Okay, so let's see. I should have stayed out in the slide. Okay, so let's actually do that. Now let's look at the effects that this makes at a more conceptual level on the topics, and we'll see how words move and how things, shift. Now we wait for this again. And what I'm going to show you is a tool. The URL is, the information's on the slide. It's doing two things. It's using a R package that's just called LDA. So it's not the topic models itself, because I'm not taking it all the way to modeling documents of topics. I'm just building and tuning LDA, right? I'll, at the end, I think, briefly wrap up on this too, but I highly recommend actually that people do this. I think another big mistake that people make functionally is that they build their model and then they do their document assignments all in one step, because all the topic model packages are so nicely built to do this for us, right? And that encourages something that is very, very, very bad. And it encourages, not with any kind of malice, and we all just sort of do it, the tuning of parameters, which is the thing that you will just hear over and over again. You say, well, how did you pick the number of topics? Or how did you pick this? How did you pick that? And they'll say, well, I just did it until it felt about right. And it's because when you run the whole thing through, you're already all the way to all of your topics, all of your documents right there. And so you start immediately asking the question, does this make sense? Does this arrange my documents into piles that I want them to be arranged into? And of course, that's what we all mostly want to write about, and that's why we started this, right? And we skip the step of actually interrogating the model itself, which you should actually do first before you ever look at your documents, right? At the full set, right? And so the way to do that is to run the LDA library. It's just LDA, which does all of the LDA stuff. And then we're also going to show you also use the library called LDA Viz, which allows you to visualize the model, right? And that it's huge. You're going to see. So right now we'll look at it. So this is an LDA Viz. Let me look where I set just arbitrarily. In this case, I set my alpha parameter to 0.02. Very, very, very low in this case, right? Which makes it, again, want to discriminate more on single word, right? When I set that up. So it's single word discriminating. And what this package does is it gives me a map, a visualization, and I will say that the XY axis here in this particular visualization isn't actually meaningful of anything other than it's just creating distance, space. It's just a convenience factor for the kind of graph that you do, right? So it's not like super meaningful distance down here and distance up in the quadrant. What's meaningful is that they are distant from each other and not together. Okay, yep. Okay, so let me go out and explain more exactly what these are, and then we'll do it. Okay, so here we go. Ignore the PC1 and PC2. Ignore the principal component for this moment, okay? What we have here is a graph that is, each one of these represents a topic cluster, okay? Every one of these is a topic cluster. Every one of these, every topic cluster, the size tells me its relative distribution across the documents that were used to build the model, but I'm not looking at the documents, right? But I fed it a set. I didn't feed it my whole set of my entire corpus, right? I sampled and I fed it that. And it's just telling me, okay, what's its overall distribution across the entire corpus, this topic. And in any individual topic, when I click on it, on the right-hand side, I see the words, the top words that make up that. And I'm not seeing the numeric probabilities, but that's based on their dirichlet distribution ranking, right? The word there. The red and the blue is because what I can see is I see an overall frequency of that word, that particular word, some its overall frequency across the entire corpus versus its frequency just in documents that you can use. Okay? It's useful to change that value. So if I change my weighting here, I can flip this all the way back and say, let's overly weight the things, the ordering of these words, so that I really care just about this. I want to ignore its frequency in other topics or all that. Pretty useful just to see this is what my topic looks like. So from here, I can click around from model to model, from topic to topic, and I can see what really are the words that comprise this one. And so here's where I would, start to say, okay, what is this about? And so that can be psychology. You can see that these are, they were lemmatized, right? So I get these weird, a lot of words. Some of these, this one's not telling me a lot. Actually, Banner, Jeopardy, Mammoth, So clearly I'm looking at some sci-fi here. And what this is, actually, the corpus is a bunch of new reviews, right, that I'm looking at. So, Prince, Smith, Brady, Chucky, this one's a horror one, right? But what I really want to point out, and so if I were working, what I would do is I would do this, and this is where I would spend all of my time here, right, with a representative sample of my entire corpus, not the whole thing, and I would build my model here, and I would adjust parameters until I got a model that looked like what I want. So that I have topics that I care about. You're almost never going to care about every topic. So a lot of times you're tuning because I want to look at as a scholar 2 or 3 things, maybe just one particular thing, right? So I have to build a model that can find that one thing, right? But then for my scholarship, I don't care about the other topics, but I'm modeling for my question. And that's crucial too. There is no generic model, really. I say that as someone who's trying to build actually a generic model for the entire early modern period. But it will serve a certain use, but it won't answer a lot, like a specific research question as much, right? But now watch what happens when I just change that one alpha parameter. So just keep in mind here, I've set it very low, so it wants to favor particular words. And we see that in the shape of the graph, right? It created a situation where this probability of the distribution really dropping off quickly. And I end up with like this very big one because a lot of words, a lot of them have the word makes and play and actors, right? And because there's so high probability there, it's sucking a lot into that universe, right? Now I'm going to change that parameter here. And in this graph, all I did was change that alpha parameter to a 0.5. It was a 0.02 in the other one, and it's a 0.5 in this one. And you can see the dramatic difference this makes in the model, right? I no longer have this dominating one, right? A lot of things have moved because they're closer to each other in terms, because there's more words overlapping. If you look at the shape, you can see it's a much more steady curve. I don't have these steep drop-offs that I had in the other one, right? I still have some at the top, but this is a different kind of long tail, right? And because of that, there's a lot more overlap of words in my topics that matter, and that creates a lot more closeness. Now here we see that PC you're talking about with this graph is basically doing a principal component analysis of the words in each cluster similarly to this graph. What's happening, right? But you can see that's dramatic. I mean, it's visually dramatic, and it is results dramatic as well, right? It is indicative of, if I see that kind of shift there, that your results and ultimately your paper, your conclusions are going to vary just as wildly, okay, based on that, right? So from here is where I really want to get back to why you should start with this, start with the LDA tuning and get in the. Oh, you know what? I think by this afternoon, I think I didn't push up the latest version. For this, I made a version that's just a script that all it does is just run this for you guys. So it's just called LDA. Or LDA models on there. LDA tuning. So you should use that. Use the script. Start with it on any corpus you're going to do. And again, not on the whole thing. Sample, take the sample, do a statistically valid sample. It's not a stats class, I'm not going to get into that, but it's easy to do. Get your text, build a model, and find the model. And you click on these. Some of them will always look like not something I care about. It's good, that's fine, right? Sometimes you'll see when though, this is the flip side of this work, where most of my work lies in this world. I'm interested actually in the ones that we look at first and think of gibberish, and realizing the computer is actually telling you that there's a semantic pattern there that you don't see. There is something there. You just don't get it. It's not wrong, right? There's this exact same math that produced this other one that you're like, that's exactly what I was looking for, right? And I'm very interested in that because I am a historian and a literature person in recovering lost topics through history. Like what we think we know what people are talking about is probably because we missed half of the stuff when we read backwards through history, right? But for most research, either way, you pick a model that looks the way you want, but that will let you find this topic that's the one I care about, right? Knowing that if you're looking at one topic that contains what you think is 3 things, then you reduce your value, right? If you're looking at, it's just not, I need to bring them together and make it bigger, right? And you find it, and then you have your model, okay? You've got a good solid model. Now you're free to take that and then use those parameters when you run the topic model, right? And now you can justify why you did that, and you haven't done the real, like, horrible mistake when doing the topic modeling, which is that since we're not actually looking at this level, what we do is we look at the papers themselves, and we look at the ones that we know, because that's what we do. And we go, did that get assigned to the topic that I think it should? Is it in the same topic assignment as these other 3? Because my paper is really going to argue that these people are talking about the same thing, and I just keep tweaking until I make that happen, right? That's not good. Right? This is and it's not necessarily bad. You can backtrace if you're good and spend time and figure out what did the model look like and all that, but better start here, okay? So this solves like we can testing our alpha and our beta parameters. Play with them all right here, no problem, okay? So again, it's the LDA model, and then this is uses the LDA library and the LDA viz library, okay? Yeah. So what I'm looking for is I'm basically going to click. First, what I'm going to do is I'm going to click across these topics and say, do they congeal? Semantically, to me as a user. So I know beyond a shadow of a doubt at this point that these words are co-occurring in their bags of words, right? And they're co-occurring according to Dirichlet algorithm, probability distribution with this shape of the distribution. Right? That's what I know. Right? So that actually is fact. It's not subject to debate, right? What I don't know is where the heuristics come in. And you look at it and say, does this grouping make any meaningful sense to me? And I do something out of it. So can I find one? I say, okay, look, number 1, that's about films. Like that's a film category, right? And if I looked, that's actually not going to be useful because these are film reviews. Let's try to find another one. Was it? Oh, it would totally be useful. It could be useful if I really wanted to say like how many people are actually. Like this could be really useful for me to decide how many just like the people that scan anything, right? You know what I mean? Like, how many of these are actually about film? It's a movie review site that we all know. With all kinds of robots and things like that. And so that's where it would be useful, just for my particular sort of more other points. So that would be useful there, but let's find ones that say world, city, lakes, human, man, star, sense, depth, story, feel, time. Okay, so I look at this briefly and say this is about what audience design, right? That's what that's about. And I find another one. If I looked around enough, I'd find one that I'm sure is about action effects, deep, summer, Godzilla, big character, water. This one is about yeah, can I label them in a way that work where those labels are effective for my customer, right?
But then the other question I have is, you mentioned involved by synthetic tension. You said that one was making consistency with the only sample of documents. Is it you not using like students but not
you can, yes, you can do that. It's but it would be better if you can validate this. Like it would be much more valid if I were really doing stuff for publication. I would read some of my corpus out, sample level, and I create two distinct purposes that I think are actually representing each other that overlap in that way. I would tune all of my parameters on one, and then I would run it with the exact same parameters on the other one. And it will never be exactly the same, but I should be able to find some similarities. It should be the same ballpark, right? You'll never be the same, ever, because of the way the DSI process works. It's the way it's in a block to it, the way that works. You'll never get identical. I could run. We'll get pretty close because the way this stuff is, I use the animus by setting the seed and forcing it to start in place and this code by design, so that we can actually get as close to people get results. In that probabilistic world, you never get identical, right? But if you get totally different, something, right? It should be recognizable. That makes sense. Okay. Yeah. I don't have a rule of thumb because so much is dependent on how many documents can I get enough to build a decent model to begin with, and that changes everything. Right? So just so people know, general rule here is that when you, it's part of this process, and I was part of the full exploratory process, part of the process that the math that gets done in all of these. In order to do the math here, it does have to calculate the work frequencies. So there's a thing behind the scenes here that's called term document inputs that almost all of these rely on a TDM or a PTM, document term input delay. Basically, I have every word by every document. And I just get these 5, 0, 1, 0, 2, 3, X, Y, Z, right? It's a big map, and this gives me my entire vocabulary. My variables are my vocabulary, right? And my documents are my observations. Okay, each document is saying, okay, in this observation, I see this one 5 times, this one 0 times, the next time, and so on, right? A general rule of thumb for this kind of analysis is that to get really good results, you can get good results with .org, get really good results. Your document term inputs should be such that you have more rows, more observations than you do. It's kind of standard statistical rule for a lot of probabilistic stuff. If you have 3,000 words in 4 documents for your observations, you are never going to get good results ever, right? So you want to check this ahead of time, and you think, well, how's that possible? Every time I have a new document, I get 1,000 more words. So not just the vocabulary is limited. There's only so many words ever possible, and there are ways for catching that. So the growth curve of this goes down with every document that you add. Fewer, it looks like this, right? Over time, it levels out. Ultimately, you get everything you've ever known, you still level out because it's just a maximum period. So you get this easier than you think. But because of that, because we're often fighting to have the numbers to get it to work at all, I would basically follow this. I would like to go to 4.5% of my corpus out, let's say, but it's often you can't. If I could, I'd pull 50%, right? I mean, I'd go and go 50-50. But I just don't have numbers, right? For me, I can't do that. It really, it can help. Yes, it can help because it gives you the dimensionality here. But if you do that and chunk that way, you see happens. If I chunk everything up, I would very quickly see that I have to go more and more topics, right? All these things are related to each other. And so as I chunk, it helps, you have to affect the team. I just know by experience if you do that, that's really it's really, right? So, but yeah, it does help. Okay, so if we, so let's real quick, because now we're running short on time, but we'll get there. Go back to PowerPoint. Let's talk about how that dirichlet allocation is actually happening. And it goes like this. It is a pretty straightforward process, although the math itself is quite complex. So we're not going to actually do the algebra here. It's a Markov cube, basically, is the process of this works. So we have our layers, and we're going through time calculating what's the probability, what's the say words part of that, right? The words belong to the topic. And let's see, fires. Okay. There's the other things we have to set are the number of training iterations, the front-end, optimization rate, and the ultimate number of topics. These three are related to the fact the Markov chains of this, and we'll do the number of topics with another kind of math and check. But basically what happens is this whole thing starts with a random seed. I've given it a probability, a prior distribution, right? So it knows that based on prior distribution, the probability distribution should look like this, right? Look like beta. It goes in and it just randomly, literally randomly assigns words to that distribution. So it matches those numbers, right? And then it starts testing. And it says, if I randomly assign words this way, right? So I put all of these words in bucket one, which is topic one, all of them in G2, G3, G4, G5, G6, and then I go back and look, do I see that those actually co-occur with each other? Right? It checks itself in that way. And then based on what it finds, it says, well, we'll do another jump, right? I'll say, okay, let's try shifting these ones. These words work, right? Because they did co-occur, so I'm going to keep those in place for right now. But these other ones are dead wrong. Let's shuffle it down, right? And let's see, and it walks its way through it. And it's, so it makes its first guess based on the priors, given the prior, boom, it does it again. Okay, now my buckets look different, right? You can see it looks different. It does it again, does it again, does it again, does it again. It keeps doing this and it keeps checking itself, and it does get better, right? Because it's keeping what works, throwing away what doesn't, trying again, and then it will stuff that worked before suddenly doesn't work so well because it actually doesn't co-occur the same way once I've gotten other things that are better, right? And so if I'm marking myself through, and this is a Markov cube, I'm moving through this chain of time, right? Until finally we get to a place of nice high probability, we'd say our high probability, right? So what it's finding actually looks like what it's seeing in the real world. And it actually goes and looks, yep, those ones are co-occurring really nicely. Yep, those ones are co-occurring. Yep, those ones are co-occurring. Yep, those are co-occurring. Okay? We call these, now it's in the Markov world, and in the topic world, we call them iterations. This is how many times do I want my topic model in my LDA code to loop again, and go again, and go again, and go again. And the number of iterations, they matter quite a bit, right? Very few iterations, it would just stop here. I wouldn't really get into my probability zone, right? I can go further. So I want to get over here, but there also is, it's a law of diminishing returns, right? I mean, that curve looks, I'm going to find that talk about myself, it sounds really what it looks like, right? And it drops off, and ultimately, it could go on iterating forever, and it will keep just trying swaps. There's a thing called perplexity that applies at various levels here, right? It's calculated. You can calculate, actually, like, where do I hit this, maximum entropy here? I mean, it's just like, there is nowhere else for it to go. It will never get any better. The topic models, notice the topic models are packaged, has a nice function that will help you just calculate perplexity. And that will give you an idea, actually, of where an optimal number of iterations, where you want to land, right? So you want to look at it, but it also, perplexity in topic models, they will also give you a nice graph on the number of topics. They calculate topic perplexity. I'm going to suggest another package here in a second that I use for that instead of using the topic model. But it's calculatable is the point, and you can really computationally, so rather than guessing and saying, oh, that sounds good, everyone said just do 1,000 or whatever, we can figure this out, right, mathematically, and roughly data drawing is true of our users, so we can trust them, right, and figure out what that number should be. The other number that's relative to that is we have optimization moments here that the mallet, one of the packages, I have a slide about this at the end, but some packages let you do this, some don't. You can set an optimization interval, like this, where it's like every 5 iterations go in and optimize, right? And what that does is it bumps itself out to another process that actually does, it's not like a back propagation, but it more fully looks at all of the steps that it's taken, how it's moving, what the overall distributions are in the text themselves, and based on that, it starts to make some better predictions about which words it might want to move next. It moves a little out of randomness, right? And so it streamlines the whole process, and like everything will get much faster. But every time I have to optimize, like these random hops get actually, better and better towards the end, right? Because it's starting to add more, really its own prior that is calculated by looking ahead. Not all the packages let you do that, but if you do, it will get you to the universe more quickly. But if you add optimization, then you're going to end up either reduce the number of iterations total because it looks better, or know that it's going to run forever, right? And the reason why this is added in is it's the computational load to try to speed these things up. Turns out that it's faster to optimize than so many months and move forward and just let it take its random walk. Okay, now the big one, number of topics, okay? Because this whole thing was predicated on K, right, which is what are the number of topics that I have? Are there 22 topics here? Are there 76 topics here? So remember with LDA, we didn't tell it what the topics were, but one of the priors, one of those 3 priors is how many topics are there, right? We have a couple methods for calculating this. I've listed on the slide deck here 3 papers. Thomas Griffiths, Finding Scientific Topics is the title of one. A density-based method for adaptive LDA model selection, and then this other one on finding natural number of topics with latent for allocation. Turns out we know from experience that better not to trust any single one. There is a 4th one actually listed, and the package I'm going to show you results from now is one that's called LDA2, and I'll list all these packages and but it doesn't. It's proven not to produce that reliable result unless under very specific consequences that are very specific situations and set of constraints. And if you find yourself in that world, then you're good and decide if you are, right? But so these are the main 3. And what this thin LDA tuning does is you send your LDA model with your parameters, right, that you set initially. But it's very smart in the sense that really all it cares about is the number of topics. It does some complexity calculations. These are fairly complex algorithms. And you tell it, go out and crawl my corpus and calculate what you think the computer is the optimal number of topics there. And what it will do is return you this graph. So it's this LDA tuning. Return you this graph of the 3 methods, or the 4 that you choose. And what you're looking for is the point of where they converge. So notice these are drawn here. This will go 0 to 1. So these 2 algorithms, their claim is that they're an algorithm that moves towards 0. The closer you get to 0, is your ideal spot. And this one is another that goes from 0 to a 1 scale. But they nicely put them together for you. It does all the math, tells you which of the algorithms to choose. And what we know from experience is that where these converge is typically your ideal number of topics, right? So what you do is you typically run LDA tuning, you get a number of topics, you run the LDA models, and the LDA viz, you get a starting set of priors, right?
you put that all together. So in this particular case, I'm probably going to take my first shot here at somewhere around 100 top, right? That's what I'm for my first guess for this particular purpose. And then I'm going to go, right? I'm going to go back now with LDA it is. Here's my number of topics. I'm going to start playing. I'm going to finesse the model itself. And then I'm ultimately going to apply it to my final corpus. And that, so let me real quickly here. So these are all the packages that are involved. To do everything that I talked about today, the ones that you need, some of these have some dependencies. They're going to involve, but the TM package, the text mining package, it'll build your term document, your TDM, and most of these other packages are pre-set up to just take a TDM corpus, it's called, a particular kind of variable TDM, and flow right in and go, right? So it's the pre-package to a lot of these. LDA, what lets me run the LDA models independently of the topic models package and the mallet package. When we're doing topic models themselves, the ones that I recommend are mallet. Mallet was kind of the industry standard for a long time. It's based on the Stanford NLP. And most everybody use that. A lot of people, myself included, are getting away from mallet. Not entirely, but mostly because it requires our Java. Because the Stanford NLP is built in Java, and Java is a pain in the ass and on. It's just hard. I mean, it's just like every update doesn't work again. The version of Java do I need? It's a bummer. I'm a Java programmer. So I started in the core NLP, work agents up there. So it makes me sad to move out of that world, but it's just hard to do and have it work well. And David Bly and his crew wrote a topic models app for that doesn't require Java, that does the LDA package the whole thing up. It's a really slick app, and I really, really like it. What I don't like about it is that it's not very open. It doesn't let you control much, right? It just assumes that you want to go with the mathematically calculated number of topics and your alpha prior to the dirichlet. And it does a lot of this up front, and it doesn't actually let you in to change it, right? Mallet lets you more in, but interestingly, mallet won't take a polynomial. I can't send a vector for both my alpha and my beta priors. It only lets me set my beta prior as a vector and not the alpha. And so I don't have total control. It's very bizarre, right? So if I want to really do it all, you got to go back to the LDA. If you really find yourself in a situation you want to do stuff, just use LDA. It spits out all the same stuff, right? It's just that you have to write the connection code, right, to do that. And I think that's really all the slide deck. I had some other topic stuff I was going to just show some real results and play around, but we're out of time, so I will stop. But I will stay here for questions, any help that people need. Again, yeah, I think I'm going to end it there and just take questions if there are. And feel free to go during questions. Before there was an LDA, this is back in like maybe 96. A group of us methods did some text classification, and we took and this was mostly Stefan Sinclair, so just to name the real people, Matt Kirschenbaum, and the major players, a project called Tapework, another funded project. And they looked at Emily Dickinson's poetry, and they tried to build a model that said, find me every erotic reference in poetry, right? And when they ran that, they got back numbers that remained consistent. LDA world, like you can see those numbers. It's just literally the top scholars in the world for poetry. And they sat them down with they scouted it, right? And just about exactly 80% of what the two films overlap. You got 100% got it right. Good. There's another 10% where they went, that is just completely wrong. Completely obviously wrong. Another 10% where they went, like, how did we miss them? We've had all of these people reading these things like over and over and over and over, and nobody ever saw that. But now that we see it, very clearly, right? So that's kind of where interest peak, and you're using that field, but the only way to prove that is to bounce it up to these human readers that are going to do what we call close reading, right? You have to go back now and take those words. You have to identify, so you have to go mark up the text itself so that it's showing you where that topic is, and you have to be very close, and you have to read it over and over again until you make a determination. Is it in the file that's gibberish, or is it in the file that is possibly needed, right?
And the package help you go back to the original text?
Yes. Yeah, I mean, thank you. But if I'm really doing this kind of thing, we use another package, like a complicated package. But this, what we do is we actually mark the documents up in something called TI, which is an XML text encoding schema. And then you can use the TI to embed all of the modeling in that. And then you can use this thing called SSLT, and web world allows us to create an interface and use parameters like the physical colors and things like that. If you have a big project, you can invest that kind of overhead. It takes a couple of weeks to get that environment set up, right? And then you kind of off the races. So if you have a big project, that's what I recommend. Like visual stuff.
So what we've been looking at, or at least since I did for topic modeling, has been to observe discourse cross-sections. Have you seen work or been involved in work where you watch discourse change over time?
Yes. So there's a lot of that work going on. It is, as one would expect, much more complicated. And there's essentially two approaches to that problem. Up until kind of right now, and I mean right now is not the last year, people started like developing algorithms. The approach was that what you did is you model discrete time segments. And that itself is used to like years, you provide historical, moments like these not good consensus. You basically build models by time, and then you line those models. You say, okay, because there's this and this is primarily right, and you can say, and a lot of that uses a lot of actually very basic distance measurements and correlation and covariance analysis, these basic statistical methods to sort of watch how these things morph and blend into each other. And so then we end up with a topic, historical time series topic map, right? We have these topics, these two topics between these other, one between two, and they're there. And so you use that information, right, to then sort of give you this longer view. You can actually say, even though there's not a single word that's the same here, 150 years later, this is exactly the same topic, right? Yeah, that's approach one. The approach that's happening more now is word embedding, where it's more of a deep machine learning, even neural net processing types of that. But basically, what you can do is you say, if you go back to first, you take the idea that a word is seen by the company of things. What you do is you say that linguistically, the only way that one topic can become another is that a particular word that's in this cluster of words, tightly clustered cluster, somebody starts using a different word, right? So instead of going to war in Vietnam or running police action in Vietnam to these other continents, so what you typically, and it proves to be relatively true, but that means people kind of do one or two word replacements in these other contexts, right? And so what we do is we're building, my prediction is that we're maybe 5 to 7 years away of having this become part of the language models, and we talk about language models, where we have these word embedding maps. We're actually watching, we're able to say this word becomes that word. It takes on this other, and when you know that, then what you can do is you take all of your text in your time series and you normalize to one version of that network that you need, right? And then you just model it. That will be way faster, actually, computation. So that's kind of the new holy grail there. And there's no actually There's nothing scary theoretically about being able to pull that off, right? It's just enough data and more grants of time to write the algorithms to do that. But it's happening on a smaller scale than but that's what you really need to be able to do. Really, and then newer is coming to play. And I will say for people that non-academic stuff, a lot of work and a lot of work now. People who are actually looking at literature, non-academic literature, that work. But it's particularly problematic. Like exactly the machines, like we paid to them. I mean, it's what it comes in, right? I mean, it's like and I'm pointing fingers at myself as well. I mean, it's what we do. Like, our whole job is to learn new knowledge. Any knowledge construct has a novel language construct. Like, so linguistic drift happens that, I mean, the speed of light in academia compared to a lot of other. Now, it's changing that to social media. Right? So, we don't have a history there yet to really know what that overall impact is, but we have enough evidence to suggest that actually Twitter and a lot of social media that persists is rapidly speeding up that making time series problem, much more. Then much harder. I mean, think about mining over 50 years, right now. I mean, it's unimaginable, like, everything post 2000, just arbitrarily, I mean, it's post Twitter coming online in 2003, like that, right? So it is a real problem, and I think we're going to have a lag. Mm-hmm. That's where we're at. Mm-hmm.